Okay, so I'm going to try and give an introduction to kriging and geostatistics. So I'm not really an expert I'm not a statistician and stuff. So it's going to be, I'm just going to try and illustrate how these methods work. Is what I'm trying to do here. So what is kriging? Basically a method for doing spatial interpolation. And I think most of us know what that means to do spatial interpolations. Basically, the process of using observations of some kind of variable at known location to estimate the value at unsampled locations. And there's a number of different methods you can use to do this. And people will maybe be familiar with linear interpolation, nearest neighbor, inverse distance, weighting interpolation. And what characterizes these are that they are all deterministic methods. So they just provide like a best estimate of the value at the unmeasured locations. So kriging is different to this because it's a geostatistical method. So not only does it provide a best estimate at the unmeasured location, it also provides a measure of what is the uncertainty or the error associated with this estimate. And that's the huge advantage of using kriging for interpolation. So how does kriging work? I think the key thing to understand is that you're basically assuming that the variable you're doing interpolation of originates or is like a spatial stochastic process. And that sounds horrible, but what it basically just means is that you're assuming that at every single unmeasured location in space that your variable is a random number that fluctuates around some mean value and fluctuates in some specified way. So what you need when you do this kind of kriging is you need to define a global mean or trend function for the variable you're considering, and you also need to define a model that describes the fluctuations and the spatial autocorrelation of the variable you're considering. And the fact is, if you can do that, that actually allows you to generate random realizations of what your spatial variable might look like in space. So that's what I've tried to show in the figure here. It's just two examples of random realizations generated with the same spatial stochastic process. And we can see that they share a lot of characteristics. So they have similar amplitude or size of fluctuations, and the period are similar as well. And we can also see that if we look at 2 points close to each other in space, so x-axis here is just the x coordinate, and up here it's the value of whatever quantity we are simulating. But we can see the 2 points close to each other have very similar values. So this suggests that there's some autocorrelation for this particular variable. So how do you describe these fluctuations? That's quite critical to kriging and to these approaches here. And or I should say, often you assume that the fluctuations can be described as a normal distribution or a multivariate normal distribution, and that this is basically described through what we call a variogram model, which is what I've shown here to the left. So this is the variogram model that was used to generate these realizations. So the variogram essentially just shows what the variance of your data is as a function of distance between the data points. So in this case here, like when we have data points that are very close to each other with a short separation distance, the variance between those points the values of those points will be very low. And we see that the variance will increase as distance between points increases. And in this case, it sort of reaches a plateau. So if you have spatial correlation in your variable, this is the kind of picture you would get. And the variogram can kind of be characterized through like a few sort of parameters, which is also what I've tried to indicate on the figure here. So this is just the value that it sort of plateaus at is called the sill. And here I've just generated two different realizations, one that has a large sill and one that has a small sill. And we can see the differences in how big the fluctuations are. That's kind of what the sill determines. Then we have the range. That's the value at which data starts being uncorrelated, basically. So it doesn't really matter once you get above the value of the range. It doesn't matter if you are, in this case, at 10-meter difference or at 40-meter difference, the variance will be the same. So they're sort of equally uncorrelated. So again, if you generate two random realizations, you can see that the red one is the one with the short sill. So we have much shorter periods, if you like, in the fluctuations, whereas the black one is with the larger scale range, where the periods are a bit longer. And finally, we have what is called the nugget effect, and that's just like what's the variability at zero separation distance. So it's kind of represents kind of micro variability in your variable, and it also, you can't really distinguish this from measurement uncertainty as well. And if you have nugget, what that just means is that you end up like with like the variable you're looking at becomes kind of discontinuous, because 2 points, even if they are separated by the smallest of distances, there can still be a difference between the values because of this nugget effect. So far, I've just been talking about how you can generate like random realizations from a stochastic process. When we talk about kriging, what we're interested in is obviously a realization that not only honor the stochastic process, but also matches our data points. So if you imagine that you just generate lots of random realizations, then from your stochastic process, then in the end, you only want to keep those realizations that matches your data. And if you imagine that you just do that millions of times, and then take the mean value of all those realizations, which is what I've illustrated here. So the black line is now the mean of all the realizations that match the data and honor the stochastic process. Then that is exactly what it means to do kriging interpolation. And if you take the variance of all those, then that's exactly the error variance that kriging provides. And obviously, when you do kriging, you don't have to do all these simulations, take the mean of them. There's equation that allows you to solve the interpolation problem. So for just the mean and the variance at every single point in space. Okay, so here I just tried to show what is the difference in the kriged values if we use 3 different variograms in this case. So actually what we see is the sill, the black and the blue has the same range parameter for different sill, but we see the interpolated value is exactly the same. So the sill doesn't actually have an impact on what the interpolated kriging value is, but it has an impact on what the uncertainty is. So we can see these are the plus minus the standard deviations around the estimated value for the blue variogram, and the black one is the one here. And the green shows the result if we have a short range. And well, yeah, it's a bit of a funny result, this, but basically what this shows is because the data points in this case are separated by 10 meters, but the separation distance, the range for the green curve is only 5 meters. It means that it automatically will draw the kriging estimates towards the mean of your the process that you've defined. Not sure that was particularly well explained. Anyway, that's just like kind of to give an understanding of what it means to do kriging. I should also say that also the kriging estimate is generally much smoother looking than the underlying process. That's also an important point, I think. So the key is then when you do kriging in practice is obviously how do you actually identify these geostatistical models that the kriging is based on, and this is what you do through an explanatory data analysis. So there's a number of things you could consider here. As I said, kriging becomes sort of, from a practical point of view, it's at an advantage if the data that you are trying to interpolate can be assumed to follow a normal distribution. So you can, like one way you can look at that is just basically do a histogram plot or a box plot, like what I've done here, of some concentration data. And we can see in this case, which is often the case with concentrations, that it's quite a highly skewed distribution. So when people do kriging and these type of analysis, it's quite common that you introduce a transformation. In this case, the concentration has been log transformed, and we can see the resulting log transformed distribution of the data is much more symmetric and normal distributed looking. So this is a much nicer variable to be working with in space for the kriging. Another thing we need to be aware of is whether there are any obvious trends in the data. So in the examples before, I was just showing how it looked if you're assuming that the global trend that your data varies around is constant. Here we have an example again of some concentration data that looks highly skewed here. And here the concentrations are plotted. This is from a transect across a plume in groundwater. And the data have been plotted as a quantile plot. So the red ones are the highest 25% of the values, and blue ones are the lowest 25% of the values. And we can see there's an obvious trend here. So assuming a constant mean for the kriging in this case is probably not a very good choice. So in this case, we could use an analytical trend model to represent the trend. And if you subtract that trend model from the data, we can see that the residuals you get are then much more, sort of follows a nicer normal distribution. And this is then what you would do the kriging estimate on. And finally, like probably the most important part of this explanatory data analysis is to try and determine this variogram. And the way you do that is you calculate an experimental variogram, and basically you just look at you calculate, I don't know how to explain this. You calculate you take all data points that are, for example, in this case here, located within 0 and 100 meters of each other, and then you calculate the variance of all those values. Then you do the same for the interval from maybe from 100 to 200 meters in this case, and calculate the variance, and from 200 to 300 and so on. And in this case, this is a nice example. We can see that the experimental variogram really displays this autocorrelation structure very nicely. And you then have to fit a theoretical variogram model, and there's a number of different models that you can use to try and capture this behavior from your data, because that's then the model you need to use in your kriging estimation. Yeah, so once you've identified a model, you can then do the kriging, and it's then good practice to try and validate your result using different techniques. I'm not going to go into huge details there, but the validation could, for example, be try and sort of remove some of the data from your data set and see how well you can predict those data points with your kriging models. So this is just a summary of the kriging. So basically, the method provides a best estimate and the variance of the variable of concern. It also allows you to do these kind of conditional simulations, as I showed before, assuming that you know or can assume a good probability distribution, which is typically assumed to be a normal distribution. As I also showed, that when you do kriging, the data you're having are actually used in two phases. So you use it firstly to do a structural analysis to identify the variogram and the structural part of the geostatistical model, and then you use it subsequently for conditioning or for the interpolation itself. And the way you identify your geostatistical model is through detailed explanatory data analysis. And here you have to be aware of, like when you do this analysis, whether your data are non-normal, whether they have non-negativity as well, like something like concentration data can't be negative. So if you start doing kriging on concentrations and you're not careful with how you define your model, you can end up getting negative concentrations, for example, or get uncertainty bounds that include negative concentration. So you have to be careful with these kind of things. Then, as I showed, the trends are important to consider. You can consider an anisotropy in your parameter or in your variable as well. And then there's a whole aspect of whether you need to remove trend or if you need to do a transformation of your variable. And if you do that, then you just have to be aware of this when you do your back transformation to the original variable. Yeah, and then finally, validation is important. And then I haven't really had time to go into like advanced applications of kriging. You can do co-kriging as well of multiple variables. So this is quite handy if you, for example, looking at how like something like, for example, groundwater levels is quite an expensive thing to measure because you need to drill bore wells and stuff like that. But you can maybe predict that quite well from topography. So that's an application of using limited groundwater level data together with topography to create a groundwater level map, for example. There's also examples of using these kind of kriging approaches for sampling design and for more sort of clever sampling design, and because you can sort of assign value of getting new information using these kind of kriging approaches. So I don't know, maybe I didn't really hit the brief with this, but that was just to try and give you a quick overview of what it means to do kriging. So that's it.
Yes.
Thank you both, Emma and Mads. Absolutely brilliant introductory material and really lovely samples, examples rather. Because it's so much easier to follow when you exemplify it. And I think Mads, particularly, I'm interested in because I've done kriging in a lot of the work over the years, and I've sort of always wanted a sort of better feedback about sampling. So you mentioned at the end that it's really important for sampling design, and this is something I always struggling with because you have all these biases. It's so hard not to be biased. So I believe in our sampling in the Indian project, maybe less so in the Thames, but certainly in Buddy, we have been kind of influenced by things. And so how can you test if you can see that you've missed a predicted area of interest from the extrapolation of the variable data? Can you then input that data, and is there some measure that you can show that you've reduced the bias? What way of proving that have you?
It's a really good question, Liz, and I have to say this is not really an area I have actually sort of been using these geostatistical methods, and before it's something I've seen So I don't think I have a really good answer for that. One thing, when you look at for example, this is just a map of some concentrations that have been mapped by kriging. So we have the mean values here, and then we have the variance or the uncertainty. What we can see is at all these dark spots, that's where we have a measurement point.
Yeah.
Around those points, we have a lower variance because of the autocorrelations in the variable. So you could say that where you have most uncertainty and where you could perhaps gain most is by sampling in the areas where the variance is high. Is a simple way, but there are like more sort of clever ways of doing this, and you could even, I've seen it in sort of in groundwater investigations, because measurements are so expensive, so you can include almost like an objective function that takes into account the cost and the likely output you might get if you drill a new borehole. Is that actually worth the reduction in uncertainty and things like this? But yeah, so I'm not really sure I have a really good answer for
that. No, but that's super helpful, and I think I'll have to spend a bit more time with the engineers. So they're not very good at sort of transferring their expertise, and you did a superb job of explaining it. So thanks very much.
So maybe one thing I would add is that when you do kriging, and that was kind of what I was trying to say with the slide here, is that the kriging estimate is always smoother than the underlying process. And what you're actually assuming is that the true variable is one of these random realizations. And obviously we'll never know which one is the correct one. So it's the kriging is just the best estimate of that. And what you often see, and I know again from groundwater application, which is a bit dangerous, is that people actually use the kriging estimate, for example, of like the permeability of the groundwater media. Then they do a kriging estimate of that, and then they use that to drive another model that relies on the hydraulic or the permeability, for example, to calculate groundwater flows or how the ground, like contaminant plume is in groundwater. And that's really quite dangerous, because there might be like a complicated, a non-linear relationship between how the kriged input is related to what it is you're actually interested in. It could also be rainfall data that you might want to drive a hydrological model. Rather than using the kriged input, it's sometimes better to use the conditional simulations to drive the model.
I think that's what I was kind of not wanting to do, but realizing it was probably going to be necessary. So I think it's absolutely essential to have models as well. And that's the key thing you always learn, is that the modeling starts at the beginning of the project, not at the end.
Yeah.
Which I do think is important for India, that because we were all a bit strapped for cash, that modeling something that it's a little bit easier to cut if you're a wet scientist. But it's the most important thing, because it really has an impact on how you do the sampling, and that's that's your essential stuff that you do at the beginning, and I think really drives the problems of bias if you're not careful. Yeah, brilliant. Thanks very much.